Hi, my name is Rohan Wagh. For my Regeneron Science Talent Search project, I developed a bacteria-powered sensor system which records soil conductivity and helps farmers gain up-to-date information on field health and water conservation. Currently, agriculture is our largest freshwater sink, using around 70% of our global available freshwater supply. In addition, overwatering and improper irrigation not only damage the soil health and sustainability of one farm, but also surrounding fields and reservoirs. So I wanted to find a way to offer farmers instantaneous information on field health to help them construct an effective irrigation plan that targets and combats overwatering and improper irrigation, especially for large crop fields. I realized that in a similar way to how we use sensors to monitor our own health, I could create a sensor system that would monitor the field health and give that valuable information back to the farmer. I created a grid of small sensors which remain planted into the field throughout the harvest season, continuously recording the electric production of bacteria. Each one of my sensors contains multiple microbial fuel cell modules. A microbial fuel cell is a bit like a battery, but the anode contains and takes advantage of electrogenic bacteria. Electrogenic bacteria are any type of bacteria that participate in electrogenesis, or the production of electric charges as part of their metabolism, as part of their life cycle. These microbes are also extremely cool because they have these protein nanowires, which are basically like arms, grabbing onto their neighbors. They're able to, as part of electrogenesis, produce charges, but then also shuttle these charges from themselves to their neighbors. Eventually, this creates a grid, kind of like our own power grid, where one electric charge produced down here can travel and make its way all the way up to this other corner, for example. The microbial fuel cell takes advantage of this ability, allowing multiple microbes from distant locations to travel to send their charges down the nanowire grid and eventually to build up on these electrodes. My sensor uses that property and measures the buildup of charge on each electrode at a different depth into the soil, and uses those values to find and estimate what the soil conductivity is of that region. That information is then sent to a central computer, which is able to look at the soil conductivity from different sensors in different areas on the field and give the farmer information on soil conductivity, sustainability, moisture, and an irrigation plan. I created an algorithm which takes that information and plots it two-dimensionally onto the field in a field map. This allows for a visual representation of all those different conditions: the conductivity, sustainability, moisture content, and most importantly, the irrigation plan and expected crop yields. This allows a farmer to, for example, look at this irrigation plan and see that they should increase watering in these areas and decrease in these areas based on what the conductivity is in that region. In addition, as certain crops grow better in ranges of conductivity, I can predict which areas of the field should be producing more crops and how to change the way you treat the field in order to achieve higher crop yields, which are these darker areas. My sensors can be installed at the start of the harvest season for around $100 per acre and stay planted and continuously providing information until after the harvest season, as composed to the existing sensor systems, which are not only labor intensive, but also temporary and significantly more expensive, at around 8 to 200 times more expensive than my sensor system. Overall, my project allows for an easy and safe solution to farm management and water conservation problems and can help revolutionize the way we farm.